Okay, welcome back to the second session of today's workshop. So our next speaker is Alessandro Nada, and he will be talking about numerical calculation of the color flux to thickness using continuous normalizing flows. And I think it will be a good opportunity to see how machine learning techniques can be applied to this kind of investigation. So please, Alessandro.
Thanks, Andreas.
Like 15 minutes, plus 5 minutes.
Thanks, Andreas, for the introduction. So this is a work made in collaboration with people in Torino, in particular Elia Cellini, who is a PhD student in our group. So essentially, I have two goals for this talk. The first one is trying to understand, trying to explain why it makes sense to do a numerical calculation of the flux tube thickness starting from the Numerical string. And the second one is to understand why we're using this continuous normalizing flow, which is a deep learning architecture, in order to do so, and why it would be better, for example, than a Markov chain Monte Carlo. Okay, so let's start from just a bit of background on effect listing theory. So we know that this is a very important non-perturbable framework that in principle provides an effective description of the confining flux tube in Yang-Mills theory. And in particular, if you look at some observer like the polycular correlator or a Wilson loop, we know that this is described in the EST framework by the partition function, okay, Z. And well, this is physically interesting, phenomenologically interesting, maybe even, because we can extract directly interquark potential from this. Okay, now there is also another observable, which is quite important, especially in discriminating which kind of string will eventually be the right one, if you want, which is the flux tube thickness. Okay. And this, from the Numerical side, I mean, from the effective string side, it's not so easy to compute analytically. Okay, so this is the first reason why we would like to compute numerically, not so much Z, which we know analytically pretty well, but this W squared. Okay, now the idea is that okay, you want to do it numerically, that's fine. Why don't we use an MCMC, so a Markov chain Monte Carlo, for example, an HMC? The idea is that it's not very good at this job. The non-locality, kind of non-locality of the FSD string action, like the Numerical action, is not very well suited for an HMC, or well, maybe an HMC could work. Indeed, maybe at the end I will show you how it works with respect to our deep learning architecture. On top of that, calculating the partition function in a Markov chain Monte Carlo is doable, but it requires quite a lot of work. And on the other hand, this kind of architecture called normalizing flows are very well suited for this job, and I will try to explain why in the second part of this talk. Okay, so this is what we are going to simulate. Essentially, we are essentially discretizing the Numerical string. This is the action that I will be using. We are literally putting our field variables on a square lattice. We are putting periodic boundary conditions in time and the in space. And I'm mentioning also that this is a kind of expansion, this trivial expansion, if you want, which gives a free boson as the first term, because it is relevant in computing the partition function itself. So we know very well the analytical solution of partition function. The point is that it's not so useful in this case because we are doing it on a lattice and it's a box. So we need a finite size solution. And this is known only for these two terms of the action. And this is not super important, but because we are not really interested in partition function, since we already know it. But we are going to use it as a benchmark somehow, as a way to know that we are doing, that our numerical calculation will be eventually correct. Okay, yeah.
I mean, this is a 3D area, right? So,
yeah.
So it has the while and all of the.
Yeah, but it should be. It should go away in the large.
Oh, you're at the large.
Yeah. Okay, so second observable, which is more interesting if you want, is the thickness of the string. And the way that we compute it numerically, this is like a snapshot of our lattice. The green points are the, if you want, a quark and anti-quark. So where we put the boundary conditions. the active points are the blue ones, and the red points are also active. So we are updating those points, and this is where you actually compute the observables, the phi squared. If you would like to do it, for example, in Yang-Mills, you would do something similar. You would have a Polyakov loop, another Polyakov loop, and then you will look at the essentially a wall sheet defined by this, and then you dislocate another operator. So it's a 3-point function. You put a plaquette somehow at a certain distance with respect to this plane. Okay, so this is kind of the same kind of operator. Okay, indeed. We know the analytical solution for the thickness in the case of the free boson, and in particular in the two regimes, the low temperature and high temperature regime. Low temperature, well, the inverse of the temporal direction, temporal size is what you would call the temperature. So this is why we're calling this low and high temperature. L is the time direction, the size in the time direction. So these are the two behaviors that we are also going to check at the end of the, when we are going to look at the numerical results. And if you want to look at an example for a gauge theory, this is a relatively simple gauge theory. It's maybe the easiest. This is a gauge theory. This is more or less what we expect in the high temperature regime. So you see that this should be linear in R, and this is what is proved numerically on the side, of course, of the gauge theory. Now we would like to do the same, but on the side of the Nambu-Goto string. This is the critical radius. It depends essentially on the string tension. Okay. Okay, so a bit of deep learning. So normalizing flows. I'm just using this because it's nice. So the idea is that you start for something which is trivial. So maybe this is just a Gaussian distribution. So something that you can manage, that you understand very, very well. And maybe you want to describe a distribution which is less trivial. Okay. Now let's look at some formulas first. This is pretty recent and also has been applied in lattice field theory in the last few years. I will comment on that later. So it's a class of deep learning algorithms. And the idea is that this normalizing flow is nothing but this invertible and differentiable function that essentially takes a prior distribution, which can be, for example, a Gaussian distribution, a trivial, or even a uniform distribution, something that you can completely control, and somehow manages to generate a new distribution called Q theta. This theta represents all the parameters of this normalizing flow. This could be millions in principle. This is where the magic on neural networks happens, which is as close as possible to our target distribution. Target distribution is, of course, the our Boltzmann distribution, ideally the one of the thing. And the interesting thing, the very powerful thing, is that for normalizing flows, you're able to write explicitly this generated distribution Q of theta. Okay, it depends on the prior and the Jacobian on this transformation. What we are going to use in the end, it's the output of this transformation. Okay, this is the final configuration phi, if you want. This should follow this distribution, and if you're lucky, if you're good enough, this Q of theta will be close enough, similar enough to the target distribution that we can actually use it in a meaningful way. Okay. Okay. Yeah, kind of. So the advantage is, in principle, if you think, for example, about lattice field theory, is that this is a tool to diffuse critical slowing down, in principle. Because if the configuration, the number you extract from the phi distribution are all uncorrelated one from another, also the final ones will be. And so if you're able to build such a flow, in principle, you're defeating critical slowing down. And this is somewhat similar also for Nambu-Goto. Maybe I will comment on that later. Of course, you need to train this. So what's the meaning of training? The training is essentially taking some quantity. In this case, it is this Kullback-Leibler divergence, which is a number somehow, which tells you how similar two distributions are. In this case, the one we are generating, and then our target. And if you manage to minimize this and bring it as close as possible to zero, then you'll probably be lucky enough that you are able to use it properly. Now, of course, the configuration that you generate with this generated distribution, this latent distribution, more properly said, are not exactly following the target distribution. So you have to correct from that. And the one way to do so is using this reweighting-like procedure. which I'm looking at here, showing you here. This O in our case will be our flux tube thickness, not to be confused with this W tilde, which is the weight. And I'm mentioning the weight because this is also very powerful, and this is also an important pro with respect to an MCMC, is that you can compute the free energy, well, the partition function directly. This is very, very powerful. You could do it in principle with an MCMC, but you need to do some cooking, okay? And in this case, it's a directed computation. This is very nice. Okay. I'm not going to comment on everything I said. I wrote here, just to say that in the last, I would say, 4 years, in the lattice field theory community, there has been a strong push to understand how to use this. There have been using several architectures applied more or less always on toy models or very, very small volumes somehow. But there is a lot of going on, and I think this is a very nice and pretty much alive part of the lattice community. The only architecture I will be mentioning today is this continuous normalizing flows, also quite recent, which we have been using. Let me just comment that one final comment is that there are several open issues in this field, more or less, mostly are concerned with how the length of the training actually scales with the volume or with the dimensions. Okay, so this is definitely non-trivial. Okay, cool. So a few words about the actual architecture we're using. These are continuous normalizing flows. The actual flow is essentially the solution of an ordinary differential equation, which is parameterized by something which is in principle arbitrarily complicated, which is this linear network V of theta. The way that you are going to actually use it in the end is that you're putting your random number generator, whatever you use to generate the prior distribution that you're using, and then well, the parameters of your neural networks, you're just inputting this to your solver for this ordinary differential equation, and you're getting the output. Okay. Okay, you're also going to need this, but I don't have time to comment on that. Let's take a bit of a closer look, just to give you an idea what V theta is. So V theta is this guy here. This K of t is a kernel with some Fourier coefficients, and this W, this capital W, is actually in this case it's a perceptron. It's the actual neural networks inside. Okay, so you can see where the actual neural networks are in this architecture. The idea is that again, you would train this. You would train again with a Kullback-Leibler divergence. You will need some time, perhaps hours, perhaps days. This depends how complicated your target distribution is. But if you're lucky enough, you're getting to you're managing to generate a distribution which is very, very close to your target distribution. A way to understand that is to use a metric, and in particular, this effective sample size. This is a number. If this number is 0, you're out of luck, in the sense that your training didn't work. But if it is 1, it's a perfect training. So Q of theta will be exactly P. Of course, this never happens, but so you want to be as close as possible to 1. But also numbers which are around 0.2, 0.2, 0.1, 0.2 could already be used. Okay. Okay, good. Let's look at some numerical results from Nambugoto. And then let's take a look immediately at this ESS, okay, at this number. This essentially tells us if our trainings are working, if our architecture is meaningful. And the answer is yes. You can see here several values. We are in the high temporal regime here, so R is much larger than the temporal size. What's happening here? Well, the ESS is okay. Several values of sigma. These are all quite large. Just to give you an idea, I mean Young-Mills sigma is 0 point something, but we are working on that. Of course, this decreases when a sigma decreases as well. And also, this is also quite easily understood. If you increase the volume, well, a probability distribution of the same theory with a larger volume is more difficult to describe. Same thing happens in the low temporal regime. A bit lower, the ESS is a bit lower, so this is a bit more complicated to simulate, but still okay. Okay, and we're also working on better architectures so that even smaller values of sigma can be simulated properly. Okay, just a couple of slides, which I'm not sure if I have not enough time to actually comment. Okay, very good. So we just rush through it. I said that before that the partition function was useful to understand whether we're doing things correctly, and this is more or less what's happening in this slide here and here. Since I have just a couple of minutes, I will just skip both and focus on the thickness. Okay. This is what we were looking. I mean, what we wanted to look at, and this is a plot for sigma equals 100. But we actually did this global fit of this rather complicated function for the thickness. These are several coefficients, most of which have some expected values. And then from the global fit, this global fit actually was quite a success for us, because all the values of this global fit are in perfect agreement with the numbers just below. And if you just pick one value of sigma, you can plot this on R with several values of L. And this is exactly the same behavior that we were looking at before, looking at this simple gauge theory. Okay, so the linear behavior, this guy here in R is satisfied, and exactly with the coefficient we were looking for. Okay, you can do a similar thing also in the low temperature regime. This is a different global fit with a different functional form. Same thing happens for these several of these coefficients, and we were, I would say, quite happy in seeing this that you can actually find a perfect agreement with what we are expecting from both the low temperature and the high temperature regime. So I think out of time. This was, in my opinion, non-trivial. The idea that we can sample efficiently the probability distribution of the Number-Goto action. Of course, we need more work to understand what's the best architecture to do so. We found excellent agreement both for the partition function and the thickness, and this essentially tells us that maybe we can trust these are kind of architectures to do numerical simulations of the Number-Goto string. And if we trust this, then we have a tool that we can use in any regime. Okay, not just low temperature or high temperature. We can literally do it at for any lattice for any size. Okay, if we're able to train it, of course. And on top of that, we can also add terms and go perhaps beyond the Number-Goto and see what happens. Okay, I think that's it. Thank you for your attention. Yeah, sure, of course. But of course, you always look at the regime in which the effective string theory is valid. So usually you don't go too close. I mean, for example, in an interquark distance, you cannot go too close. At some point, this breaks down. Yeah, that will break down, and you're not allowed to use. Yeah, you're not allowed to use it anymore. Of course, yes.
But nothing stops you.
No, of course not. Yeah, sure. In principle, yes. But you cannot connect anymore with the Yangi's.
Looks like your model is
yeah, so there's most. For the low temperature, I'm not completely sure why it works worse than well, it might be depend actually just from the fact that I think here just the volumes are just larger. Okay, and well, lower string tension means we are essentially getting closer and closer to a critical point, and this becomes more and more complicated for the neural networks to understand what is going on. Essentially, yeah, if you want the correlation length are getting bigger and bigger, and so the neural networks has to understand how to connect points which are further away in space. And Yeah, but they're also very difficult for a Monte Carlo, right? So these, in a Monte Carlo, you see this from the point of view of integrated autocorrelation time. The autocorrelation times explode, right? On the side of a normalizing flow, you would see that the training times explode. Now the question is, and this is a kind of an open question, which explodes faster somehow.